Imagine our entire universe is just a thin slice, a membrane, floating in a vast, higher dimensional space, occasionally bumping into other universes to create big bangs. What if every tiny decision you make, every quantum flutter, actually splits the entire universe into multiple copies, each with a different outcome playing out simultaneously? Some physicists even theorize that our three-dimensional reality could be a giant hologram, with all its information encoded on a distant two-dimensional surface, like a cosmic TV screen. Number 14. The universe, that's just a big computer program. Ever get that weird feeling that something isn't quite right, like a tiny glitch in your everyday life? Well, some thinkers, like philosopher Nick Bostrom, and even physicists exploring the fundamental nature of reality, have pondered a truly unsettling idea. What if our entire universe, everything you see, feel, and know, is actually an incredibly advanced computer simulation? This isn't just a cool sci-fi movie plot. It's a serious hypothesis with some brain-bending implications. The idea known as the simulation hypothesis suggests that a civilization far more advanced than ours could have created our reality, perhaps as a research project, an experiment, or even just for entertainment. Think about how far our own video games and virtual realities have come in just a few decades. If you extrapolate that progress over thousands or even millions of years, creating a simulated universe seems less like fiction and more like an eventual technological capability. Physicists like Silas Bean have even tried to figure out if we're living in a simulation. They've looked for clues like whether the laws of physics in our universe have a kind of underlying grid or resolution limit, similar to the pixels on a screen. If space-time isn't perfectly smooth, but made of discrete points, that could be a hint. The bizarre part. If this is true, then we might be characters in someone else's program. Are we conscious beings? Or just very sophisticated artificial intelligences that believe we are conscious? Are there programmers watching us? Could they intervene, change the rules, or even shut the whole thing down? The resources needed to simulate an entire universe down to the quantum level would be astronomical, but for a sufficiently advanced civilization, it might be trivial. It makes you wonder about the ultimate nature of reality. If our universe is simulated, is the universe of our simulators also a simulation? Could it be simulations all the way up? Number 13. Worlds born from black hole bellies. We think of black holes as cosmic vacuum cleaners, places where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon. But what if, instead of being dead ends, black holes are actually cosmic wombs, giving birth to entirely new universes? This is the core of a mind-bending theory called cosmological natural selection, or the fecund universes theory, proposed by physicist Lee Smolin. Smolin took inspiration from Darwin's theory of evolution by natural selection and applied it to cosmology. His idea is that when a massive star collapses to form a black hole, the singularity at its center, a point of infinite density, doesn't just sit there. Instead, it bounces and expands to create a new baby universe safely hidden from our own, perhaps with slightly different fundamental physical constants. Here's where the natural selection part comes in. Smolin proposed that universes which produce more black holes will in turn produce more baby universes. If the physical constants can change slightly with each new universe, then over many generations of universes, those whose constants are openated for producing black holes, and thus more stars, more galaxies, would become the most common. It's a kind of cosmic evolution. Our universe, with its particular set of physical laws and constants that allow for stars, galaxies, and black holes to form, might be the way it is because it's fit in this cosmic evolutionary sense. Truly bizarre implication is that our own universe might have been born from a black hole in some parent universe, and every black hole in our universe could potentially be a gateway to, or the seed of a new universe. We are, in a sense, living inside the result of a previous cosmic birth, and our own black holes might be continuing this cosmic lineage. It makes you wonder what those other universes are like, and if they too are teeming with stars, planets, and perhaps even life, all shaped by this grand evolutionary process spanning realities. Number 12. The looking glass universe that ran backwards before ours. What came before the Big Bang? It's one of the biggest questions in cosmology, and it usually leads to a kind of conceptual dead end, since time itself is thought to have begun with the Big Bang. But what if the Big Bang wasn't a beginning, but more like a turning point? Physicists Latham Boyle, Kieran Finn, and Neil Turok from the Perimeter Institute proposed a radical idea. A universe existing before ours, which was essentially a mirror image of it, running backward in time. This antiverse theory is built on a fundamental symmetry in physics known as CPT symmetry. CPT stands for charge, parity, and time. Charge conjugation means swapping particles with their antipocals, like an electron for a positron. Parity transformation means inverting spatial coordinates. Time reversal means, well, running time backward. The laws of physics as we know them are believed to be CPT symmetric, meaning if you apply all three transformations, the physical laws should look the same. Boyle, Finn, and Turok took this idea and applied it to the entire cosmos. They proposed that the event we call the Big Bang was a moment where a universe dominated by antimatter, contracting and running backward in time, reached a point and then bounced or transitioned into our universe, now expanding, dominated by matter and running forward in time. So from our perspective, the antiverse would appear to be an antimatter universe shrinking towards the Big Bang, while from its perspective, we would be the antimatter universe shrinking towards its Big Bang, running backward in its time. It's a mind-bendingly symmetrical picture. One of the neat things about this idea is that it could potentially explain the existence of dark matter. The theory suggests that a very heavy type of right-handed neutrino, a sterile neutrino, might have survived from this CPT symmetric epoch, and its properties could align with what we observe as dark matter. The bizarreness lies in imagining this other cosmos, a perfect reflection of our own, but made of antimatter and with its arrow of time pointing in the opposite direction, existing on the other side of the Big Bang. Number 11. Reality's extra rooms. In F, theory's 12 dimensions. You've probably heard about string theory suggesting that reality has more dimensions than the three spatial ones: length, width, height, and one time dimension we experience. Typically, string theory talks about 10 dimensions. But what if even that isn't enough? Enter F theory, a branch of string theory developed by physicist Kamran Vafa. Theory doesn't just stop at 10 or 11 dimensions, like M theory, another extension of string theory. It operates in a framework that effectively describes physics in 12 dimensions. Now, before your brain melts, these extra dimensions aren't like the ones we walk around in. They are thought to be incredibly tiny, compactified or curled up at an unimaginably small scale, much smaller than an atom. Think of a garden hose from far away. It looks like a one-dimensional line. But if you get very close, or if you're an ant walking on it, you realize it has a second, circular dimension. Theory uses complex mathematical tools, particularly something called elliptic fibrations, to describe how these extra dimensions are structured and how strings and branes' higher dimensional objects, predicted by string theory, behave within them. The F in F theory playfully stands for father, as M theory is sometimes said to stand for mother. The bizarreness of F theory lies not just in the sheer number of dimensions, but in the incredibly intricate and abstract mathematical landscape it proposes as the foundation of our reality. These extra dimensions, though hidden from us, would govern the fundamental forces and particles we observe. The specific way these 12 dimensions are shaped and interact could determine why our universe has the specific laws of physics it does, like the strength of gravity or the masses of elementary particles. Trying to visualize 12 dimensions is practically impossible for our brains, which are wired for a 3D world. But physicists use the language of mathematics to explore these far-out possibilities, hoping to find a theory of everything that unites all known physics. Theory, with its extra-dimensional playground, is one of the more exotic contenders. Number 10. The universe left-handed twin, hiding in the mirror. Have you ever wondered if there's a mirror version of you, living in a mirror world where everything is flipped? This might sound like something out of a fantasy story, but a version of this idea was seriously considered by physicists Songnao Lee and Chen-Ning Yang back in the 1950s. They were grappling with a puzzle in particle physics related to the weak nuclear force, one of the 4 fundamental forces of nature. Experiments were showing that the weak force didn't always behave the same way if you looked at its mirror image, a property called parity violation. It was as if the universe had a subtle preference for left-handedness or right-handedness at the subatomic level. To try and restore a kind of cosmic symmetry, Lee and Yang initially speculated, what if there was an entire mirror universe out there, identical to ours, but with its parity flipped? In this mirror world, left would be right and right would be left. Perhaps the fundamental laws of physics were perfectly symmetric, but we just happened to live in one version of the universe, while its mirror twin also existed. Particles in our universe that appeared left-handed in their interactions with the weak force would have right-handed counterparts in the mirror universe. While this specific idea of a complete mirror universe existing separately isn't the mainstream explanation for parity violation today, the standard model of particle physics incorporates parity violation directly. The concept itself is wonderfully bizarre. Imagine a whole other cosmos, a perfect reflection of ours, where its inhabitants, if any, would see our universe as their mirror image. Could such a universe interact with ours? Some more recent theories have explored ideas of mirror matter that interacts with our matter only very weakly, perhaps only through gravity, making it a candidate for dark matter. The sheer philosophical weirdness of a perfectly flipped reality coexisting in some way with our own, even if only as a theoretical construct to explain a subatomic quirk, highlights how physicists are willing to entertain truly strange dimensional possibilities to make sense of the cosmos. Number 9. Cosmic fountains, spewing matter from another place or time. We all know about black holes, those super-dense regions of space-time where gravity is so intense that nothing can escape. But what about their theoretical opposites? Enter the white hole. Proposed as a valid mathematical solution to Einstein's equations of general relativity, just like black holes. A white hole is a hypothetical region of space-time that cannot be entered from the outside, but from which matter and light can escape. Think of it as a cosmic geyser, or a fountain constantly spewing out energy and matter. But you can never fall into it. While black holes suck things in, white holes would, in theory, explosively push things out. The bizarreness factor here is huge. Where would all this matter and energy coming out of a white hole originate from? One wild idea is that white holes could be the other end of black holes, forming a structure called a wormhole. Matter falls into a black hole in one part of the universe, or even one universe, and gushes out of a white hole in another part, or perhaps even another time or a completely different universe. This would make white holes gateways to other realities or different epochs. So far, we have no observational evidence for white holes. In fact, many physicists think they are purely theoretical, and unlikely to form in nature because their formation would seem to require very specific, unlikely conditions, or they might be incredibly unstable. However, some recent, highly speculative theories have suggested that the Big Bang itself might have been a kind of white hole event, or that certain mysterious ultra-high energy cosmic rays or gamma-ray bursts could be signatures of tiny primordial white holes, finally erupting after a long period of dormancy. Imagine if our universe was birthed from a colossal white hole, or if smaller ones pepper the cosmos, occasionally acting as unpredictable conduits from somewhere else entirely. The very idea of a place you can't enter but which constantly ejects the unknown is a deeply strange dimensional concept. Number 8. Our entire universe is just a fancy projection. Imagine that everything you see around you, the stars, the galaxies, even yourself, isn't real in the way you think it is. What if our three-dimensional universe is actually a kind of hologram, a projection of information that's stored on a distant flat, two-dimensional surface? This is the mind-boggling essence of the holographic principle, a concept that emerged from studies of black hole thermodynamics by physicists like Gerard 't Hooft and Leonard Susskind. The idea started when scientists noticed something weird about black holes. The maximum amount of information a black hole can contain, its entropy isn't proportional to its volume, as you might expect, but to the area of its event horizon, its two-dimensional surface. This was a big clue. It suggested that the information content of a region of space might actually be encoded on its boundary, not throughout its volume. The holographic principle generalizes this idea to the entire universe. It proposes that everything that happens in a volume of space can be described by a theory on the boundary of that space, which has one fewer dimension. So our 3D universe plus time could be a holographic projection of physical processes taking place on a 2D surface, far, far away perhaps, at the cosmological horizon, the edge of the observable universe. This doesn't mean we're living in a literal laser light show. It's about information. The amount of information needed to describe our universe perfectly could be stored on a surface with fewer dimensions. Physicist Juan Maldacena provided a concrete mathematical example of this principle with his ADS CFT correspondence, which connects a theory of gravity in a certain kind of five-dimensional space-time, anti-de Sitter space, to a quantum field theory, conformal field theory, on its four-dimensional boundary. This correspondence has become a powerful tool for physicists. The bizarre implication is that the 3D world we experience could be an illusion, a very convincing hologram generated by physics happening on a lower dimensional screen. It challenges our most fundamental intuitions about space and reality, suggesting that dimensionality itself might be more fluid and less fundamental than we ever imagined. Number 7. When cosmic sheets slam together to make a bang. The Big Bang Theory tells us our universe started from an incredibly hot, dense state and has been expanding ever since. But what caused the Big Bang? One of the most visually striking and bizarre alternate dimension theories is brane cosmology, particularly the ecuratic or cyclic universe model, developed by physicists Paul Steinhardt, Neil Turok, Justin Curry, and Bert Everett. This theory draws from ideas in string theory, which posits the existence of extra spatial dimensions and brane's membrane-like objects that can have various dimensions. In this picture, our entire universe is a three-dimensional brane, a three-brane floating within a higher dimensional space, often called the blue. The ecuratic model proposes that the Big Bang wasn't the absolute beginning of time, but rather the result of a collision between our brane world and another brane world moving through this higher dimensional bulk. Imagine two colossal, universe-sized sheets slowly drifting towards each other in a hidden dimension, and then BAM, they collide. The immense energy released in this collision heats up our brane, creating the matter and radiation we observe, effectively resetting the universe and kick-starting a new phase of expansion, what we perceive as the Big Bang. The cyclic part comes in because these collisions could happen repeatedly. After a collision, the branes might move apart. Our universe expands and cools as it is now, eventually becomes empty and cold, and then the branes might be drawn together again for another collision, leading to an endless cycle of cosmic death and rebirth. This is a radical departure from the standard inflationary Big Bang model. The bizarreness lies in picturing our whole reality as just one slice in a larger unseen dimensional arena, subject to colossal cosmic fender benders with other parallel universes. It means there are dimensions beyond our perception, and within those dimensions, other universes, branes, might exist potentially with different physical properties. Our beginning, and perhaps our end, could be dictated by these interdimensional encounters. Number 6, the secret fifth dimension that tried to unify physics. Long before string theory started talking about 10 or 11 dimensions, a couple of mathematicians came up with a surprisingly elegant idea to unify two of the fundamental forces of nature using just one extra dimension. Back in the 1920s, Theodor Kaluza and Oskar Klein independently developed what's now known as Kaluza-Klein theory. At the time, physicists knew about gravity, described by Einstein's general relativity, and electromagnetism, described by Maxwell's equations. These seemed like two separate forces. Kaluza had a brilliant insight. What if space-time wasn't just four-dimensional, 3 space plus 1 time, but actually 5-dimensional? He wrote down Einstein's equations for gravity in 5 dimensions and found something amazing. When you mathematically reduce these equations back down to 4 dimensions, you not only get Einstein's original theory of gravity, but you also naturally get Maxwell's equations for electromagnetism. It was as if electromagnetism was just a manifestation of gravity rippling through this hidden 5th dimension. Oskar Klein later refined this by proposing that this 5th dimension wasn't large and obvious like the others, but was curled up into a tiny circle, so small that we couldn't detect it directly. Imagine a straw from a distance. It looks like a 1D line, but up close you see it has a 2D circular surface. Klein suggested this 5th dimension was like that tiny circular part, existing at every point in our familiar 3D space. The bizarreness here is twofold. First, the idea that there's a whole extra spatial dimension all around us, just too small to see, is pretty wild. Second, the notion that one of the fundamental forces we experience daily, electromagnetism, responsible for light, electricity, magnetism, is actually just gravity doing a dance in this hidden dimension is a profound conceptual shift. While the original Kaluza-Klein theory didn't fully succeed in unifying all forces, it didn't incorporate quantum mechanics or the other known forces, like the strong and weak nuclear forces. It was a revolutionary idea that laid the groundwork for modern theories involving extra dimensions, like string theory. It showed physicists that thinking outside our familiar dimensional box could lead to surprising new insights about the very fabric of reality. Number 5. Reality woven from tiny vibrating strings in hidden dimensions. One of the most famous and famously bizarre attempts to create a theory of everything is string theory. At its heart, string theory replaces the idea of fundamental particles, like electrons and quarks, being point, like dots, with something even more fundamental. Tiny, vibrating, one-dimensional strings. What we perceive as different particles are, in this view, just different vibrational modes of these fundamental strings, like how different notes on a violin string are produced by different ways it vibrates. But here's where the extra dimensions come in with a vengeance. For string theory to work mathematically and be consistent with what we know about quantum mechanics and gravity, it requires that the universe has more spatial dimensions than the three we experience. Most versions of superstring theory, which incorporate a symmetry called supersymmetry, need a total of 10 dimensions, 9 spatial dimensions, and 1 time dimension. Theory, an extension that unifies various string theories, operates in 11 dimensions. So where are these 6 or 7 extra spatial dimensions? Like in Kaluza-Klein theory, they are thought to be compactified or curled up into incredibly complex tiny shapes called Calabi-Yau manifolds at every point in our familiar 3D space. These shapes are so small, on the order of the Planck length, about 10 raised to the power of 35 meters, that we can't directly detect them. The bizarreness is staggering. First, the idea that the fundamental building blocks of reality are not particles but unimaginably small vibrating loops or segments of string. Second, the existence of these extra dimensions, not just 1 but 6 or 7 of them, intricately folded up and hidden from our senses. Precise shape of these compactified Calabi-Yau manifolds is crucial because it's thought to determine the vibrational patterns of the strings and thus the properties of the particles and forces we observe in our universe, like the mass of an electron or the strength of the electromagnetic force. Finding the right Calabi-Yau manifold that reproduces the physics of our specific universe is one of the biggest challenges in string theory. It means our reality, with all its laws, could be a consequence of the geometry of these hidden, higher dimensional spaces. Number 4. Our universe is just one bubble in an infinite cosmic foam. The Big Bang model describes the expansion and evolution of our observable universe. But what if our universe is just a tiny part of something much, much larger and weirder? This is the picture painted by the theory of eternal inflation, developed by physicists like Alan Guth and Andre Linde. Inflation itself is a widely accepted theory that proposes a period of extremely rapid exponential expansion in the very early universe, just fractions of a second after the Big Bang. It helps explain why the universe is so flat and uniform on large scales. Eternal inflation takes this a step further. It suggests that while inflation ended in our particular patch of space, allowing our universe to form and evolve, the process of inflation continues in other regions of a much vaster meta-universe or multiverse. Imagine a cosmic ocean of space that is, on the whole, always inflating. Within this inflating ocean, little bubbles can randomly stop inflating and form pocket universes, each with its own Big Bang, its own expansion, and potentially even its own different physical laws or constants. Our universe would be just one such bubble in an infinite sea of other bubble universes. The bizarreness of this concept is hard to overstate. It implies that there could be an infinite number of other universes out there, each potentially vast, each possibly having different fundamental properties. Some might be similar to ours, others might be wildly different, perhaps with different numbers of dimensions, different fundamental particles, or different strengths of forces, making them sterile and incapable of supporting complexity or life. We could never reach these other bubble universes because the space between them is eternally inflating, expanding faster than the speed of light, effectively isolating each bubble. The theory of eternal inflation arises naturally from some of our best models of the early universe, but its implication, an endlessly proliferating foam of universes, is a truly mind-altering vision of our place, or lack thereof, in the grander cosmic scheme. Means the universe, as we know it might be, just an insignificant droplet in an infinite cosmic ocean. Number 3. Everything mathematically possible is actually real somewhere. This one takes the concept of alternate universes to its most extreme and abstract level. Physicist Max Tegmark, proposed a hierarchy of 4 different levels of multiverses. While levels I, and I deal with regions beyond our cosmic horizon, universes with different physical constants, like bubble universes, or the many worlds of quantum mechanics, it's his level, the 4th multiverse, also known as the mathematical universe hypothesis, MUH, that is truly mind-bending. Tegmark suggests that at the most fundamental level, physical reality is a mathematical structure, and not just our universe, but any self-consistent mathematical structure that can be defined also corresponds to a physically real universe. Yes, you read that right. Every possible mathematical system, from simple geometries to incredibly complex abstract algebras, things that mathematicians could invent or discover, describes its own separate universe existing just as concretely as ours. Our universe, with its specific set of particles, forces, and dimensions, is just one particular mathematical structure among an infinite ensemble of others. The bizarre implication is that concepts like existence and mathematical consistency become almost interchangeable. If a universe can be described by a complete and consistent set of mathematical rules, then it exists. This means there could be universes with entirely different kinds of physics, perhaps based on mathematical systems that bear no resemblance to the ones we use to describe our own reality. There could be universes based on cellular automata, universes with different numbers of dimensions, universes where logic itself works differently, as long as it's internally consistent. Why is our particular mathematical structure, the one that describes our physics, the one we find ourselves in? Tegmark speculates that perhaps only certain complex mathematical structures can support self-aware substructures, like us, that can observe and ponder their reality. The MUH is a deeply philosophical idea, rooted in the observation that our physical world seems to be incredibly well described by mathematics. Takes this unreasonable effectiveness of mathematics to its ultimate conclusion. Math isn't just a tool to describe reality. Reality is math, and all math is reality. Number 2. The universe that clones itself with every quantum choice. Every time you make a decision, even a tiny one, do you ever wonder about the road not taken? What if that other path, and indeed every possible path, actually happens in a separate, parallel universe? This isn't just a philosophical musing. It's the startling consequence of the many worlds interpretation, MW, of quantum mechanics, first proposed by physicist Hugh Everett III in the 1950s. Quantum mechanics, our best theory of the very small, is famously weird. It says that particles can exist in a superposition of multiple states at once, like being in several places simultaneously, until they are measured, at which point they seem to randomly collapse into just one definite state. Everett found this collapse idea unsatisfying. He proposed that the collapse never actually happens. Instead, every time a quantum measurement or interaction occurs that could have multiple outcomes, the entire universe splits into multiple copies. In each copy, one of the possible outcomes becomes reality. So if an electron could be here or there, the universe splits into one version where it's here, and another where it's there. And you, the observer, also split, with one version of you seeing it here and another seeing it there. This happens constantly for every quantum event throughout the cosmos. The number of parallel universes being created every microsecond is unimaginably vast. The bizarreness is almost overwhelming. It means there are countless versions of you, living out every conceivable alternative life path, stemming from every quantum divergence. There's a universe where you chose a different career, one where you said yes instead of no, one where that random subatomic particle swerved left instead of right, leading to a cascade of different events. These universes are all equally real, existing in parallel, but they generally don't interact with each other after they split, so we can't visit them or even detect them directly. The MWI resolves some tricky conceptual problems in quantum mechanics by doing away with the mysterious collapse, but it does so at the cost of an extravagant proliferation of worlds. It forces us to reconsider what I even means if there are infinite copies of me experiencing every possibility. Number 1. All of time comes at once, and we just stumble through it. We experience time as a flowing river, moving from a fixed past through a fleeting present into an unknown future. But what if this perception is just an illusion? What if all of time, every moment from the Big Bang to the ultimate end of the universe, already exists, laid out like a vast four-dimensional landscape? This is the concept of the block universe, an idea that grows out of Einstein's theory of relativity. Special relativity showed that time is not absolute but is relative to the observer, and it famously unified space and time into a single four-dimensional continuum called space-time. In the block universe view, this space-time is a static, unchanging block. All events, past, present, and future, have an equal claim to reality and are simply different locations in this block. Past hasn't disappeared, and the future isn't unformed. They are all just there, like different points on a map. Our sense of time passing and the specialness of now is seen by proponents of this view as a subjective feature of human consciousness, not an objective feature of reality itself. The bizarreness here is profound. It means that the dinosaurs still exist in their space-time location. Your future self, perhaps, reading these very words years from now also already exists in its space-time location. Free will becomes a tricky concept in a block universe, as all events are predetermined in the sense that they are already part of the fixed space-time block. It's like characters in a novel. Their entire story is already written from beginning to end, even though they experience it scenely. This view also makes the flow of time an illusion. There's no cosmic now that is objectively special. Every moment is equally real. While deeply counterintuitive to our everyday experience, the block universe is a straightforward implication of the geometry of space-time and relativity, and many physicists find it to be the most natural interpretation. It suggests that the dimension of time is far stranger than we imagine. Not a river we travel along, but a vast, already existing landscape through which our consciousness creates the illusion of passage.